we present BenchMR, a motion planning benchmark for wheeled mobile robots. There are many components in the motion planning pipeline, ranging from the planning algorithms and extend functions, to the environments on which they are evaluated. Finding a best performing combination of these ingredients for the desired use case is therefore a challenge. BenchMR enables the evaluation of such planning approaches specifically tailored to wheeled mobile robots, supporting applications in service or intralogistics robotics as well as autonomous driving. Our benchmarking suite provides a high-level interface via Jupyter Notebooks that allows the user to easily set up new scenarios and obtain informative insights on the performance of the planning algorithms and the quality of the found solutions. BenchMR is expendable and we already support different motion planning backends, such as OMPL and SBPL out of the box. We support many different environment types, including procedurally generated environments. In addition, many planning techniques and extend functions, as well as other components in the planning pipeline are provided. Closest to our work are the following benchmarking frameworks. OMPL provides a benchmarking tool that applies to any robotic system and is focused on a more generic evaluation of the planning algorithms, whereas we specifically focus on applications in wheeled robotics, such as parking or warehouse navigation. The Moving AI benchmark provides various grid environments, such as the city's dataset, which we also support in this work. It focuses on grid-based path planning and does not account for the kinodynamic constraints that wheeled mobile robots impose. The Common Road project provides various scenarios related to lane changing which are typically encountered in autonomous driving. Our focus is on motion planning in static environments where longer-term plans need to be found. In the following, we give an overview of BenchMR. The main functionality is implemented in C++. There, we interface with external libraries, such as OMPL and SBPL. We supply different implementations of the planning components, including the extend functions, optimization objectives, and post-smoothing algorithms, among others. In addition, different scenarios and metrics are implemented to evaluate these components. The configuration of benchmarks happens through JSON files which provide a human-readable interface to set up reproducible experiments. Although it is possible to directly define experiments via the C++ code, or the JSON configuration, it is often more productive to leverage a higher-level programming language to access such benchmarking functionality. Therefore, we provide a Python interface where the user can set up new scenarios and configure experiments. The Python layer communicates with the C++ backend through the JSON configuration files. When an experiment has finished, a JSON file containing the results is generated and consumed by the Python interface. Through Jupyter Notebooks, BenchMR provides an easy-to-use environment where the user can plot and analyze the results as soon as they become available. As part of the motion planning components, we provide different types of environments. Polygon-based environments represent obstacles as convex polygons, which can be loaded from vector graphics files, such as SVG files. Grid-based environments represent obstacles as grid cells that are either occupied or free, and can be loaded from grayscale image files. We also implement various techniques of procedurally generated environments. Occupancy grids resembling corridor-like environments can be randomly generated for different corridor sizes and complexities. Furthermore, random grids can be generated with a defined occupancy ratio. For polygon-based environments, BenchMR supplies a generator for asteroid fields, where convex polygons can be automatically generated at random to represent obstacles. At the core of BenchMR are the motion planning algorithms. We support sampling-based motion planners from the Open Motion Planning Library. These include the feasible planners, such as RRT or PRM, as well as asymptotically optimal planners, such as RRT star or PRM star. For all sampling-based planners, we support the sampling from a uniform distribution or a deterministic sequence, such as Halton sequence. Besides sampling-based planners, we additionally include lattice-based planners from the search-based planning library. These include algorithms, such as ARA star or MHA star that find a path by constructing a graph where motion primitives connect the vertices. Extend functions are used by sampling-based planners to connect consecutive states on a path. We support robot dynamics models for a kinematic car and a kinematic single-track model that account for a two-dimensional position plus yaw angle of the robot. The typical car steer functions, such as Dubin's and Reed's Shep, are included, as well as the continuous curvature steer function and POSQ for differential drive robots. For the state lattice-based planners from SBPL, we include car-like motion primitives as well. Post-smoothing methods improve the path found by the motion planners. We provide interfaces to the following algorithms from OMPL. B-spline, which fits a spline through the vertices to smoothen the path. Shortcut, tries to skip vertices on the path to connect them directly. Simplify Max combines B-spline and shortcutting. Finally, gradient-informed path smoothing, or GRIPS, moves vertices on the obstacle distance field gradient and uses shortcutting to smoothen the path. By default, the motion planners try to minimize the path length while searching for a feasible solution. Optionally, the user can also select other optimization objectives, such as smoothness, where the angle between consecutive path segments is kept as small as possible. Another objective is the curvature normalized over path length, which minimizes the curvature of the path segments between path discontinuities, also known as cusps. Finally, the clearance can be maximized, so that the distance to the nearest obstacle at each point on the path is as high as possible. In many path planning libraries, the robot is assumed to be a point, which simplifies the collision checking against obstacles. To bring BenchMR closer to real-world mobile robot applications, our default collision detection is based on polygons. As shown on the right, the robot can be represented by convex polygons which are tested for collision with both grid-based and polygon-based environments. We use the separating axis theorem for efficient collision checking between convex polygons. Having found a solution, for each path that is processed through BenchMR, we compute a variety of metrics. Besides path quality metrics, such as path length, curvature, smoothness, and number of cusps, we also summarize the computation time by the different planning phases, such as collision detection and the evaluation of the extend functions. BenchMR is expandable by the user to support more metrics as well. Let's take a look at an example on how to use BenchMR. In the following, we will run our software through a Docker container which automatically has all dependencies pre-installed. We provide detailed instructions on our website on how to install and run BenchMR. Having started a new Jupyter notebook, we first import the motion planning benchmark package named MPB. We construct a new MPB instance that stores the benchmarking configuration and provides various helper functions to set up and run experiments. First, we define to use the procedural environment generator for corridor-like grid environments. Next, we select the motion planner's RRT, RRT star, and informed RRT star, to include in this benchmark. As extend function, we configure the reads shep steer function. Finally, we run each planner 5 times on different procedurally generated environments. After the benchmark has completed, the print info command shows us a summary for each of the 5 runs. As can be seen, all 3 planners found solutions which were exact and non-colliding in each environment they were evaluated in. While we ran our little benchmark, BenchMR generated 3 files. The log file contains a trace of the standard output and standard error file descriptors to which the C++ back-end process has written. Such information can be helpful in debugging problems from the back-end which may not always be communicated to the Jupyter Notebook front-end. The config.json file stores the entire settings that are necessary to define a benchmark. We could have also generated such file by hand, but our Jupyter frontend makes this much easier by exposing helper functions to Python which will translate the user commands to such a configuration file which is consumed by the C++ backend. Once the benchmark has finished, a results.json file has been created. It stores statistical information over all the metrics available in our software suite from each run that has been executed. Furthermore, it contains the benchmarking settings and various other metadata to ensure the results are reproducible as much as possible. Let's get back to our benchmarking notebook and visualize the paths found by the 3 planners that were run. By calling visualize trajectories, we can plot the 5 different environments with their start and goal configurations, as well as the solutions found by the planners. Various settings can be made to this and many other high-level functions in BenchMR, which we document on our website. Next, we can visualize various metrics that were gathered during the benchmark by calling the plot planner stats function. Here, the violin plots aggregate the results from the 5 runs of each planner. They show the path length, normalized curvature, angle over length, computation time, mean clearing distance, and the number of cusps. Finally, the bar plots show the number of exact and collision-free solutions in relation to the number of total runs. In our next experiment, we run the informed RRT star planner on a larger procedurally generated corridor environment. This time, we assign a maximum computation time limit within which this anytime planner has to return a solution. We set the limit to 10 seconds through the max planning time option. The visualized path indicates that the planner found an exact solution that connects the start and goal node in this environment. When we reduce this time allotment to just 0.5 seconds, we see that informed RRT star is unable to find an exact solution. Similarly, for a 1-second time limit, this planner returns a path that does not successfully connect the start to the goal node. Now let's assume we want to execute these different configurations in parallel, so that we can efficiently gather feedback on the performance of the planners under various constraints. To leverage multi-process parallelism, we provide an additional component, named Multiple MPB. This component allows the user to add different MPB instances and execute them in parallel while adhering to limitations on the number of parallel jobs and the memory usage, as defined by the user. In this example, we want to run informed RRT star over different maximum planning time limits. Therefore, we create 3 MPB instances with time limits of 0.5, 1 and 5 seconds. We add these objects to the multiple MPB container, which we then execute. Once all benchmarks inside multiple MPB have finished, we are presented with an aggregate plot of some high-level statistics on the planning outcomes. As expected, the 0.5 and 1 second time limits were too short to yield exact solutions, whereas 5 seconds was enough for informed RRT star to find a successful path. Multiple MPB simplifies merging of various planning results and offers many other features, which we document on our project website. In our next tutorial, we use a grayscale map image as the grid environment in which the planners are benchmarked. We supply 2 example images in PNG format on our BenchMR project repository. Let's use the Intel Lab environment. We define the map dimensions to be 150 grid cells, which means the image will be scaled to fit within the desired size while maintaining its aspect ratio. The occupancy threshold defines the boundary below which darker pixels will be treated as occupied cells. With an occupancy threshold of 0.5, we see that the grid map is missing a lot of occupied areas. By changing it to 0.98, we see the grid map has the desired shape and can be used for further experiments. In our final tutorial, we will use a polygon-based environment. BenchMR supports such types of environments in the form of SVG files in which the obstacles are represented by convex polygons. These vector graphics files can be easily generated in Inkscape, for example. Let's choose a warehouse environment and change the geometry of the robot to a square-shaped warehouse robot. We see that both planners found a solution and the new robot shape is visualized at every few steps on the path. Next, we change the collision model of the robot to a point. Intersection tests between a polygon and a point are fast to perform, but since the robot has no actual size in this model, we do not recommend it for realistic applications. By default, collision checking in BenchMR is polygon-based. We now demonstrate in detail some experiments where BenchMR provides useful insights about the behavior of sampling-based motion planners. In a first example, we compare different sampling techniques. Namely, we compare the behavior of the PRM algorithm using the deterministic Halton sequence and the uniform distribution for sampling states. The experiments show the advantages of using deterministic over random sampling. PRM with Halton samples achieves better performance in terms of path length, normalized curvature, planning time, and the number of cusps. In another experiment, we benchmark the motion planners on environments of varying complexity. We investigate how different planners perform by varying the obstacle density or the width of the corridors in indoor-like environments. As an example, we plot how the number of cusps of the paths of different motion planning algorithms using the Reed's-Shep steer function vary with the environment complexity. Here, we change the minimum corridor width for random indoor-like grid-based environments and the percentage of blocked cells for random grids. We can see that the number of cusps significantly decreases for almost all motion planning algorithms as the corridor sizes become bigger. On the other hand, the number of cusps goes up for almost all motion planning algorithms as the percentage of blocked cells increases. BenchMR allows us to use different combinations of feasible motion planners and post-smoothing algorithms. Such combinations have rarely been thoroughly evaluated and compared against asymptotically optimal planners. In this experiment, we show such a comparison and analyze the performance of those two classes of algorithms in terms of path length and normalized curvature. The comparison is performed using the Reeds-Shep extend function. In these figures, we can see that feasible motion planning with post-smoothing can indeed outperform asymptotically near optimal motion planning algorithms in both planning efficiency and the resulting path quality. For example, RRT using the post-smoothing algorithm Simplify Max, shown in the center, achieves a smaller path length, and about the same normalized curvature, after less than 1 second, while informed RRT star, shown on the right, finds a solution after 60 seconds. In another experiment, we compare the different combinations in random indoor-like grid-based environments, using the Reeds-Shep steer function. As we can see from the figures, the post-smoothing algorithms, GRIPS and Simplify Max often significantly decrease the path length and maximum curvature, with Simplify Max typically running faster. The post-smoothing algorithm B-spline does not always improve the path quality, which might be due to the issue that B-splines do not translate well to paths that can be followed by Reeds-Shep and other steer functions, resulting in slight turns that increase the curvature. In our final experiment, we show how BenchMR allows us to analyze the behavior of a sampling-based algorithm by varying the optimization criterion it is using. In the top row, we visualize the trajectories resulting from 3 different optimization criteria, namely path length, minimum clearance, and normalized curvature. These solutions have been found by PRM star and evaluated on 5 different procedurally generated corridor environments. In the bottom row, we report the statistical results from PRM star using these 3 different objectives. The figure indicates that maximizing the minimum clearing distance indeed increases the clearance compared to minimizing the path length or normalized curvature, but also increases the number of cusps substantially. Minimizing the normalized curvature, on the other hand, decreases the curvature slightly compared to minimizing the path length. With the goal of comparing a large set of state-of-the-art motion planning techniques, we presented BenchMR, the first open-source motion planning benchmarking framework designed for sampling-based motion planning for non-holonomic, wheeled mobile robots. The framework is available as open-source package, with more details and documentation on our website. In future work, we aim to extend our benchmarking suite to dynamic environments, to support even more realistic autonomous driving scenarios. Thank you for your attention.